Welcome to Cryptography and Hardware, the 10th session. Up to now, you learned how to partially implement symmetric ciphers and also hash functions, and particularly focused on SHA-3 and Keccak. Now, we are slowly move toward public key cryptography, and we focus actually on the adders, how to implement the adders, which are the main components of most of the public cryptography or public crypto algorithms. I guess most of you are familiar with public key cryptography, but a very, very short overview of why we need public key cryptography. I mean, you already learned that symmetric cryptography, like the AES and triple DES, are pretty fast, and they are also very secure, but we have the problem of the key distribution. Means that if the secret key, both parties need to have the same secret key, and this should be transferred securely. We don't have a secure channel, otherwise we use it. No, we need a secure channel to transfer the secret key, and then afterwards communicate via that secret key. And then number of keys in a network between many users is a lot. That if we have n users, then we need n by n minus 1 divided by 2 keys, or for each pair of the users, and then it becomes pretty hard when the network grows. And also, there is no way to guarantee, or let's say to prove that somebody has done something. Yeah, it means that if Bob and Alice are communicating with each other, they can cheat each other. Yeah, means that they can, because they have identical key, then some of them say you sent this, and the other one says, okay, you also sent this, and so on. Yeah? Then we need some form of functionality to provide non-reputation, to provide non-repudiation. Now, symmetric cryptography, you notice you have two keys, public key and secret key. Key public and key private. And then how it works, public key is sent by one body to another body, or made it public. And then through the encryption, we use the public key. And then through the decryption, we use the private key. Yeah? Then the problem of the key distribution is solved. Keep in your mind that this does not solve the problem of the authentication. Yeah, means that by this, you still need some other functionalities for authenticated encryption, yeah, that we are not actually dealing with in this lecture. And there are different security mechanisms that you already, I guess, learned through some form of some lectures like Introduction to Cryptography. You need key distribution for Diffie-Hellman key exchange, for example, or the RSA, that you don't need a pre-shared secret key, and non-repudiation and also digital signatures will be also provided by some schemes like the RSA, by DSA or ECDSA, and it provides also message integrity. And for the identification, you need some challenge response protocols with digital signatures, and digital signatures are provided again by this public key cryptography. And you can also have encryption and decryption like the RSA or Al-Jamal. And the disadvantage of all these schemes, is that they are computationally very, very intensive. Almost 1,000 times slower than symmetric cryptography, for example, the AES, triple DES, and so on. And the basic key transport protocol, the thing is, as I said, is super slow, usually. And what you do, you usually use the asymmetric cryptography to just do the key exchange. And the key is exchanged for the symmetric schemes, and the encryption, decryption, and the communication are done afterwards with the symmetric cryptography, which is pretty fast, that you have already learned, like block ciphers or stream ciphers. This is an overview of the key length and the security levels, that how much security you had. For example, with 64-bit security in the symmetric cryptography, there are still symmetric crypto algorithms like the lightweight crypto algorithms that they use 64 bits, and then it's equivalent to ECC with 128, and ECC is electric cryptography, and equivalent to RSA with 700 bits. Up to For example, AES 128. You can say that, okay, with a long-term security, you need 256 bits for the ECC and more than 3,000 bits for the RSA. I mean, it's also very hard to say the exact complexity of RSA and Diffie-Hellman, because it's difficult to estimate how hard is the factorization or factoring. But of course, I mean, you know about the quantum computers and the trend at the moment that the quantum computers may show up soon, or in the future, and then we should be actually prepared for that. But I mean, it may take 1 or 2 decades to have them, and some, I mean, physicists may say, okay, they have some also doubt whether they will ever exist, who knows, because there are still problems in realizing them in physics, with a large number of qubits to be able to, for example, break one RSA with 3,000 bits, for example, or ECC with 256 bits. Then for that reason, of course, the research is ongoing for post-quantum cryptography, to build something that if in the future we have quantum computers, we still don't have any algorithm to run on them, to break, for example, one's other public key crypto algorithm, like Kyber or lithium or something else. Okay, you definitely know this, but they are just some review that how the encryption and decryption of RSA works. You need N, which is the P multiplied by Q, and P and Q are large primes. And the encryption is X to the E, and decryption is Y to the D. If X is the input and Y is, for example, the ciphertext here. What you need to do this is just modular exponentiation, because everything should be modular N. This is the only thing that I want to give you through this slide. That everything is just exponentiation, modular exponentiation. And how to implement this? And the problem is that, as I said, everything is modular exponentiation, and it's actually then simple scheme, but it's hard to implement this, and it's because the numbers are pretty large. I mean, for example, 3,000 bits each operand has, and when implementing the RSA, particularly on constrained devices, I mean, if you want to write software, for example, for smart cards or microcontrollers, then we have to pay close attention to the correct choice of the arithmetic algorithms. How do we implement actually this modular exponentiation? Otherwise, the implementation becomes very, very slow. I mean, you already learned probably a square and multiply algorithm, which is fast. It has its own problems, but at the moment, as a basic concept, it's just square and multiply, that you have h as the input exponent and x as the element that you want to compute as x to the h modulo n. And then you go through all bits of h, h2, ht to h0. And then you go for all the bits. And then every loop you do the square, and then based on this bit you perform the multiplication or not. And everything is again modulo n, means that the y does not grow. I mean, every step you just keep it modulo n. This is something that I guess you already learned if you have passed any simple course in the areas of cryptography. And then there are speed-up techniques, like selecting a short public exponent e, which doesn't harm the security, and also CRT, China's Riemann theorem, and exponentiation with some pre-computation. This is also something which is also possible. Now, other solution or other alternative is ECC, or elliptic cryptography. The problem or the motivation for ECC is that the RSA needs to deal with very large numbers, and then computational overhead is pretty high, and then you can consider how many servers in internet, and then they have to perform this, and then all the time with how many users and how many times per second, and then how much power we are just losing because the RSA uses very long or large exponents. Then that is, of course, the motivation. The solution is ECC or elliptic curve cryptography with much smaller operands, or for example, 160 bits to 256 bits. The computation of the elliptic curves, I need to explain this, that the elliptic curves are polynomials that define points based on this simplified equation. Y to the 2 equals x to the 3 plus a, x plus b, and of course for the parameter a and b. That they define this shape. If you change a and b, that's just this shape changes. And then on the real numbers and the parameters a and b, here you have y2 equals x to the 3 minus 3x plus 3 over r, which is the real numbers. And then these elliptic curves can be also defined over the finite fields. For example, we have Zp, from this field, which is integers of 0 to p minus 1. And then over this field, you can actually define here the same thing. And with this condition that for a to the 3 plus 27 to the b to the multiplied by b to the 2 does not equal 0 modulo p. There are definitions for that. If you are interested to know how and why, then probably need to search for it or look at one of the references which were defined in the first section of the lecture, Understanding Cryptography, then to understand why this is the case and why this condition should be fulfilled. Now, the thing is, every point, which is called P, is like this, and then this is actually symmetric over the axis X, and then minus P also is available on this curve. If P is on the curve, minus P is also on the curve. We need one more point, imaginary point here, as the infinity, which does not exist on the curve, but we have to consider it because we want to, for example, say P plus something equals P. And then we have to define something like this. Then there are some computations like point addition and point doubling. You can see here there are definitions that here point addition means that if you add them, you get something like this. You make a line over P and Q and see where it actually collides with the curve, and then you project it over the X to get P plus Q, and the point doubling is roughly the same, but both points are here. Then you need to make a point like this over the point, line this over the point, and then again project this to get 2P, which is the point doubling. And then there are also some formulas for that, for the point doubling and point addition. And then you need to deal with this y1 and x1 and also y2 and x2, which are the coordinates of these 2 points, to get y3 and x3, which are the 2 other coordinates, which are the coordinates of the resulting value. What you see here again is something just adding the points, adding the values or subtracting, and then also there is a division here. Division also, modulo P, need to also be implemented by multiplication. Because we are everywhere we are in ZP means that integer field of size P. This is a similar algorithm to square and multiply, that again you look at every bit of the scalar D, and then what you do here you do point doubling, and here point addition to represent actually this T equals D multiplied by P, and D as a scalar. This is required for the ECC. elliptic cryptography. Yeah, this is something that you similar to encryption and decryption that you have for the RSA, which is exponentiation. Here you need to multiply it by, for example, d. I mean, you have the point p, you need to multiply it by d. And then this is a similar algorithm for similar to square and multiply, as I said. The point here is that for implementing the RSA and elliptic curve, and also some former hash functions like SHA-1 and SHA-2, I mean, we have seen SHA-1 shortly in the previous session. For all of them, you need actually addition. Yeah, I mean, you need modular exponentiation, and modular exponentiation needs modular multiplication and also squaring, and that needs addition. And for elliptical cryptography, both point addition and doubling need modular multiplication. Yeah, and in this modular multiplication need again addition, yeah, or adder. And for SHA-1, you directly need modular addition. And SHA-2 the same. I mean, Ketchak you have seen, it's not based on any arithmetic operation, and it doesn't need any adder. Now, we need to review what you have learned probably during the first or second semester digital technique. Yeah, the adders. I mean, you already learned the full adder, that you have A, B, and C as the input, and S is the sum result, and C is the carry out. And you consider Ci as the carry in, the next one is the carry out. Yeah? This you already learned. And this is, of course, the lookup table or true table, and then you can say that Si is just XOR of all of this, and carry out is just at least two of them are 1. Yeah? I mean, that even two of them are 1, then you should have carry out as 1. Now, how do you implement a larger adder? You just connect these full adders together after each other, which is called Reaper carry adder. You know, means that here this is the LSB of A and B, the bits of the A and B, and the bits of the A and B, yeah, 4 bits. And then carry in, for example, you say 0, but doesn't matter, you can select also like carry in, and then you have 4 bits output with a carry out. Yeah? This is the simplest way to build the adder, which also works very well, but it's super slow. Yeah? Means that it needs any instances of the full adder, and carry may actually passes from LSB to the MSB. Means that the critical path delay of the circuit is pretty long, particularly if you just imagine that in RSA you have 3000 bits. No? The adder then has a lot of, I mean, if you implement it in hardware, then it takes an ages till really then addition is completed. Yeah? That means that the maximum clock frequency of your circuit becomes extremely low. And then the solution is, yeah, write sum of product of sum of the adder. You can write that, but if you have 3000 bits, then good luck. Yeah, this is not easy and trivial to write. Then the full adder, let's see just the carry propagation, how this works. These are the formula of, I mean, you already learned the half adder, I mean, before at half adder that you can build a full adder with 2 half adders. Yeah, means that you have A and B as the input and carry in, then you give it to 1 half adder, which is just XOR and AND, and we call here the full adder output PI, which is the XOR, and GI, which is the AND. Yeah? These 2 formulas. And then we say the output, the S, which is the sum, again is the XOR of the carry with the PI, and here again another formula which is the OR, yeah, between this guy, the GI, and the result of the carry with the result of the carry with the PI. Yeah, PI and carry go to here the AND, and then it generates here. One more thing that you should consider is that this OR, yeah, you can also implement with XOR. Yeah, I mean, it doesn't matter. I mean, you can also have the XOR here. It never happens that both of them are 1. Because if this guy is 1, yeah, definitely PI is 0. And this makes it here 0. Yeah, and then you can have here XOR. Yeah? Good. Now, based on this, the carry look-ahead adder is generated. Means that if you look at here, we define Pi as AI XOR BI and GI as AI and BI. And then imagine, and suppose that here we write here the C1 equals G0 plus P0 C0. Again, I get back here. This was the formula, yeah. Ci next carry is the GI or PI CI. And here it is. Next carry is G0 plus P0 C0. And you can write the same for C2, G1 plus P1 C1. And the same for G3, G2 plus P2 C2. And then write the formula based on just P and G. Yeah? Because you can look at here, you can replace here C1 with something which is based on just G and P, yeah, and of course one carry in, carry 0, and here you can write it directly just based on G and P and the carry in. The same here, instead of G2, I mean G2 is clear, P2 is okay. Instead of C2, you can write this guy. And then you have the formula of C3 only based on P and G and carry. Yeah, imagine that you already built the P and G. I mean, if you remember, the formula for P and G were completely individual for every bits. Means that because P was the XOR between A and B, and G was the AND between A and B, means that at one certain delay, you have all the P and G completely independent of the size of the adder. Now then you go through this combinational circuit to directly generate the carries. Yeah, and then you can also generate the sum. Yeah, how you can generate the sum? Look at here, the P, yeah, I is XORed with CI to generate the sum. Means that if you have the carries, then you can easily directly XOR them with the corresponding P and get the sum. This works like this. Suppose here in this module is the carry look-ahead adder, which receives P and G and generates the carries. And then here the carries are generated, and then they are XORed by the corresponding P. C0 with P0, C1 with P1, C2 with P2, and so on. Then you have the C for the carry out and the sum values. Now this is already good, I mean 4-bit adder, but if you look at here, you see the circuit for the C0 is small, for C2 becomes larger, for C3 becomes even larger, and so on. And then you will end up with many gates, many inputs getting to a very large gate here. I mean, the AND gates becomes larger for the larger steps. For example, if you have even 32-bit adder, then the AND gate that you have there that needs at least 32-bit input, and the same for the OR gate. Then this becomes even larger. I mean, for 4-bit, for 8-bit is okay, but for larger than that, it's not really efficient. It becomes even, again, slow. Then Koge and Stone, two researchers, many years ago, developed a concept which is called Koge and Stone adder. Some of you already learned this. This actually avoids the drawback of carry look-ahead adder. How this works? This is the general structure of an n-bit parallel prefix adder. And carry look-ahead adder is one of them. This is a general form. Now you look at here. This is generating just P and G, if you remember. P and G for every bit individually. And this is the part which generates the carry. And the carry is just XORed with the P, to what? To generate the sum. And all of these kind of adders are called parallel prefix adder. And carry look-ahead adder was one of them, with just saying, okay, how to generate this prefix tree. And Koge and Stone adder is the same. Koge and Stone adder doesn't deal with the pre-computation and the post-computation. It just says you how to make this prefix tree. That's all. Yeah? The first part is actually, as I said, this pre-computation is the same as carry lookahead adder. This is just defining P and G. But how here we give one more index. We call them also P1 and G1 at the level of 1. We call them at level of 1, P1 and G1. Of course, with index I means that this is index I equals 0, index equals 1, index I equals n minus 1. And then we call each of them, each pair of P and G as GP. And GP 1 and I means actually this guy and this guy. Yeah, good. Now you see here that the pre-computation module, if you want to implement this, you can, to ease the implementation, you can assume that Cin, the incoming carry, you can also see this as an incoming input as another bit. It means that you can consider as the LSB, and then you have, instead of n-bit input, you have in total n plus 1 input, to ease the implementation, because you can see that Cin and 0 are coming here to be added together as the first bit. Then it's easier to interpret that. You need to say that G is actually Cin and P is 0 directly. Then you need to interpret this part just differently, and then it helps you to build the next layer easily. Then for that, if you look at here, P1 and G1 are actually considered the first one as here, and then instead of n P and G, we have n plus 1 G and P. This is something that you should keep in your mind. Then we have n plus 1 pairs of P and G, not n pairs. Now the Koga-Stone adder, the only difference to the other parallel fix tree adder, or the other kind of the adders that I explained, like carry lookahead adder, the only difference is actually here that the GP pairs are actually coming here. You see them from index 0 to 16 if it's 16-bit adder. Again, as I said, 17 different pairs. And then you have to use different modules here. Some modules are red that you see here, that are border GP generator, and the blue ones are the full GP generators. What they do, they receive 2 G and P, then generate another G and P. They receive 2 GP, generate 1 GP. But the other one, the red ones are simpler, than the area of the circuit is smaller. But what is important here is that at every step, you need to shift. Now you can say that the step or layer 1, we are here, and we receive the GP of this column and the one column before, for all of them. And here in the next layer, the difference between the GPs that receive every GP generator, the distance is 2 columns. Here the distance is 4 columns, and distance is 8 columns. It means that every time is just multiplied by 2. Or if you have a layer index, then you can imagine that you have actually layer index, then this is 2 to the index of the layer. The distance between the GPs which are arrived here. One strange thing that you see is that here, that there is one extra here, and the reason is because of the carry in, means that we consider that the carry in also as another input, and then instead of 16 GPs, we have 17 GPs, and then we have 1 extra layers for that. This is one of the differences. If you can also imagine that there is no carry in, there is no carry in, then you don't need to actually have n plus 1 GPs. Just with n GP will still work, and the number of layers that you have will be also reduced. Good. Now, the inside of the GPs, I mean, why Koga and Stone reached this construction? I mean, it's not hard. You need to write down the formulas and you end up with this. Yeah, but this is was very innovative scheme. Yeah, but we don't try to get how to get these formulas. I mean, it's just to say that these blue GPs or full GPs, they have just and OR operation, and the border GP generators are simpler, means that yeah, you have just AND and OR, yeah, just 2 gates, the other one has just 3 gates. And of course, I mean, you can imagine that these gates can be also implemented more efficiently. I mean, if you are able to say that, okay, I use here the inverted input and here the inverted output and inverted input, and then this one is also inverted, then you can use the NAND gate here, and then instead of here one OR gate with 2 inverted input, then you can use one NAND gate. Yeah. Of course, I mean, if you implement this, and the synthesizer will anyway try to synthesize it with lower number of gates and the gates which are smaller. Yeah, but manual optimization is also possible. Yeah, this is just the original formula and the equations from the Koga-Stone adder. And the final step, I mean, this was something that you already learned, that they carry out. I mean, just they are XORed with the P from the first layer, and then you have the sum and also the carry out. You know, this is simple. And again, this is the full construction. Yeah, how you build the Koga-Stone adder. And one important thing that we did not discuss much is the number of layers. Yeah? The number of layers that you have is here. If you consider carry in as a separate input, then you need log 2n plus 1. I mean, if you completely ignore the carry in, I mean, say that my adder doesn't have the carry in, then you will have just log 2 of n layers. Yeah, it means that if you consider this as one element in every layer, you know, that how much is the delay between after 2 gates like this, and at most log 2 of n of these components will be after each other, and this is the minimum up to now that you can do. You know, it means that the Koga-Stone adder is considered as the design which with the very, very affordable and reasonable area requirement, at the same time with pretty low latency, you know, with a very good critical path delay. Means that even if you have 2 bits to add, each one is 256 bits, no? Then the maximum of the gates that are coming after each other is just 8. You know? 8 of these modules will come after each other, and the critical path delay would for an AND gate for adder with 256 bits is pretty good. Yeah. Good. Now, what else? Now, you have seen that sometimes in the implementation you need to also do subtraction. Why? Sometimes you need modular addition. And for modular addition, you need to check whether this is larger than something or not, and then to subtract it from the modulo. Then for that, you need a subtractor. I mean, a subtractor you can also implement easily. Yeah. I mean, you already learned 2's complement and 1's complement, and 2's complement is just 1's complement plus 1. And then what you can do, you have one extra input to say that, okay, this means, hey, I want to do the subtraction, and then you invert by this all of the bits of the second operand, like here, B, and then you need to also plus 1, and the plus 1 can be used using the carry in. And it doesn't matter if this is a carry look ahead adder, is a carry ripple adder, is a Koga-Stone adder. It doesn't matter. You have an adder which doesn't have, I mean, it has an input as the carry in, and then you need to use this carry in for the signal to define whether or to say that you want to do the subtraction. But then at the same time, you cannot have the carry. Yeah, it means that you cannot say that, okay, this addition can also have an extra carry in. Yeah, then the carry in is used directly for this. Yeah. Then you can do also subtraction. And we just review some VHDL. I mean, this is out of the Vivado, because it's just very simple things, and I have them in the slides. I mean, if you want to just add, I mean, very simply, I mean, they are again for first, second semester bachelor, that you have the full adder. This is the definition of the full adder: A, B, carry in, S, and carry out. And then you want to write an adder with 4-bit. I mean, here again, generic, means that the parametric is defined, means that you can set n to anything and it should work correctly. What you have, you just instantiate full adder how many times, n times, and then you tie the carry in of the, or carry out of the previous module to the carry in of the next module, and so on. Then you generate the sum and also the carry out. Super simple. The next one is here the same way. You have 4-bit, 4-bit as the default for the n. And what we do here, we generate P and G and SI. I mean, this is the same way, but this is somehow a carry look-ahead adder. Means that P and G are generated, and the S is also PI, X or the carry, and the carry is always the PI or GI, and then again P and carry, and then XOR or with G. Yeah, of course this doesn't say that it's definitely optimized, and as I said, then when you have n large, then this part becomes very slow and large, and this is the job of the synthesizer, how to build this. Now something else that you can easily do, then you can actually leave this to the synthesizer. No? Here what I have, of course I need to use a numeric STD library for that. And then what I do here, I think in one of the other designs I have shown you, I have used this. No? Then you concatenate this with 0, A and B, because you need to also have the carry out. And then you just add them. You just add these values by plus, because they are defined as unsigned. You see here unsigned. You can also have signed values, but it doesn't matter. And then what happens, then the synthesizer will do everything for you. Now, the synthesizer understands that you have an adder here. And most of the time, at the moment, the synthesizer are using Koga-Stone adder, by default. I mean, they have some template inside that then they understand that you have an adder, and then to implement the adder, they use the Koga-Stone adder. Of course, not for the FPGAs. I mean, the Xilinx FPGA, they have also a carry look-ahead adder, if you remember. Inside every slice, there are some components that they are actually built for the carry of the adder. And then they use these modules which are inside to implement the carry in or the adder in a more efficient way than compared to other forms of the adders. If you want to build the adder and subtractor, this is the same way. You have one module as sub, it's one signal as sub, defining whether you want to do the subtraction or not. And then here is just saying that when the sub is 0, then B is invert of the B or not. And then you have also adder with the carry in, and the carry in is a sub, and that's all. Now, then the only thing that you need to care about, because we will see in the next session, when you want to build a multiplier. Why you need the multiplier? Because for the ECC, or you need what? You need exponentiation, modular exponentiation. You need a modular multiplication. Then you need to have an adder, and the adder should be fast, should be should have a very low critical path delay, and this is the main module that you need to build. And then how about modular addition? As I said, we need modular addition as well, because you need to for the modular multiplication, you need modular addition. Otherwise, you have to otherwise that the size of the result just grows. Now you need to every step just keeping it at every step you need to keep it modular n. And here again is a very simple way to do that. I mean, using again the synthesizer, and the synthesizer will define or decide how you wanna how the multiplication, how the addition and subtraction should be implemented. Yeah, you define here also the modulo and the number of bits. AV and BV, I mean, they are just concatenated with 0, and MV is here M, yeah, the modulo, the generic. And then R1 is just A and B are added together, and then the result of this is also minus, subtraction between this. And it just checks whether the result of this subtraction has a carry or not. Yeah, means that it performs anyway the subtraction, because you should consider that this is a fully combinational circuit. Now it doesn't have any clock. Yeah? Subtraction will be performed anyway. You just look at the output of the subtraction and check whether the subtraction had a carry or not. If the subtraction had a carry, then means that the value is negative. Means that the value that you subtracted from the modulo was smaller than the modulo. Yeah? Then you check. Then what you select the R1 as the output instead of R2. Yeah? Then this is the multiplexer here. And then by some, again, functions, you need to turn back this RV, which is assigned values, which is assigned or unsigned value to a steady logic. Yeah, one more thing that you have to consider, this is super important, you have to turn them to the sign now instead of unsigned. Now look at here, everything here was unsigned. No, it doesn't matter. But here, when you do the subtraction, you need to consider this as the signed. And then this is actually the sign value that we are adding, you know, because we are dealing with everything with the positive values, but then for the sign bit, we need to add one more bit and consider and define them as assigned, and then do this addition and subtraction, and then looking at the most significant bit, which is actually the sign bit here. Yeah? And you may say, why, when it's 0, yeah, then we take actually this guy. Whether the result is negative or not. If the result is positive, you know, the sign bit is positive, means that this is still positive, and then you can take this. Otherwise, you can take the other one. Because this is exactly the sign bit.